Welcome everyone to this week's lecture. Today we want to talk about classification, which is a bit different than regression. So these are the two types of problems we usually deal with in data science. Either we try to do a regression or we try to do a classification, but there is still some overlap in these two problems, which is why we can use the regression we've learned before, so linear regression, with a bit of different techniques to do classification problems. So let's talk about a standard classification problem using, for instance, the iris dataset, which is a really famous dataset, which basically everyone who has dealt a lot with R has seen at some point because people always use it. It contains data on three different species of flowers, so it's dealing with the iris setosa, iris versicolor, or the iris virginica. I don't know if I pronounced this correctly. In any case, these are two different species, different flowers of the species iris. I think iris is the species, or the species in at least is iris setosa, iris versicolor, and I think the family is called iris. I'm not completely sure. I'm not that familiar with flowers or with biology in that sense. In any case, here we see different measurements of their sepals or their petals. And for instance, we could see here that if the petal length that was measured is less than, say, 2.5, then we can be pretty sure that we're dealing with a flower of species iris setosa, because basically we only see these measurements in that species. And that would be like a really simple classification rule. With the help of an observation, so with a measurement in this case, we can classify our flower as iris setosa in this case. And this is a classification problem, and we want to make things a bit more simple, so we want to deal with a binary classification problem. So instead of looking at this data set, we transform it a bit. We make it have only two variables or two groups. Either it is iris setosa or it isn't, or it's one of the other two. And in this lecture we want to find out how we can make this more, how we can do a classification more mathematically or more statistically, instead of just looking at this picture and then using some rule of thumb. I don't know, it's less than 2.5, I will classify this as iris setosa. We will, in some form, we want to use linear regression to do it. And here you might be inclined to do linear regression in the form of just using the factor or the group labels, which is 0 or 1 in this case. We've transformed it that way. This is a numeric variable, so we could technically use it as a response for a linear regression, and then simply use petal length as a regressor for this linear regression. And with that we could possibly classify, fit a model and use it to classify our flowers. But this is usually the wrong way to do classification, because as you can see here, if you try to do it and you take a look at the predictions from that model, you will see that of course the linear regression won't deliver 0 or 1, so our group labels back to us. So it will always be some floating point number, and we can also not really interpret this number. You might be inclined to say, okay, if it's values between 0 and 1, we will just say it is the what we get from our linear regression is the probability to be iris setosa or be not iris setosa, for this flower to be of that species. And the problem with that is that our linear regression is not bound to the range of 0, 1. So as you can see here, we can also have negative values, and this completely destroys our interpretation of probabilities. So we cannot directly use linear regression for our classification because of these issues, that we are not really bound to one specific area. And what we could instead do, which is the, so to speak, the gist of so-called generalized linear models, or GLM, is to transform the response. So for instance, we could look at the logistic function, which just takes any real value and transforms it to the range 0 to 1. And then these transformed values we could possibly interpret as probabilities, and with these probabilities we could classify our observations into the specific species. So in this case, if we for instance have fit a linear regression or fit a linear model and then get a prediction that we can transform using the logistic function and obtain a probability of say 0.9 that our observation belongs to a flower of species Iris setosa, then we could say, okay, classify this observation as being of species Iris setosa. This is generally the idea of a generalized linear model, so to take a linear regression and transform it, but it is not exactly the same thing. You can think of it in this way, but it's not exactly the same, so let me try to go into a bit more details about this. So in ordinary linear regression, we always fit a distribution. So we say our response y is equal to x beta, where x is our design matrix, plus the residuals epsilon. And these are IID random variables which have a normal distribution. And so here we have clearly stated the whole distribution of our response variable, and the consequence of that is that the expected value of y given an observation x is simply the linear model, or is simply this the linear combination of x and beta. So x here is possibly not only a single value, it could be using more than one predictor. So this is a vector, and if you write it out, it's just a regular expression that you're used to from linear regression, using more than one predictor. And again, that the expectation or the expected value given the observation is equal to the to this linear form is the consequence of us having defined that the distribution of our response is given in this exact form, which is also a normal distribution here. And notice also that the other way doesn't really work the other way around. So you cannot say, I know that my expected value given an observation is a linear form, so and I can then conclude that my response variable is a normal variable. This of course I cannot do. And in a sense, this makes this ordinary linear regression a bit more restrictive, because in the end we are only really interested in the expected value. So what generalized linear models do is they don't set out at this part, or they don't start here. They start out saying, okay, my expected value given an observation of my response variable, or my expectation of my response variable given an observation is of this form. This is what generalized linear models do, and they go even a step further. They don't simply say the expected value is exactly this linear form, or also called a linear predictor. It's not exactly the same, but there is a relationship between those two. And this relationship is typically described via a function. So here we say that the g of our expected value is simply eta, which is just this linear predictor. And this function g is what we would call the link function. And of course, if you use a one-to-one function, then you can invert it, and then you can simply equivalently state this as the expected value is given as the inverse of our linear predictor. So here you can still use the idea of ordinary linear regression. You still want to use the linear predictor, but then you transform it. And what you get is the expected value of a response variable. This is a bit, in theory, it's a bit different than just stating this and then transforming it. But the idea, I think you can, is still given by do a linear regression and then transform the response. There is a bit of theory behind this for which distributions of our response variable this works. It's not important right now, and this is why I don't want to go into details. I've written it out in a bit more details in the lecture note, But the important point is that this works for if for y our response variable is, for instance, a normal variable, then we have if we use our link function as just being the identity function, then we just have ordinary linear regression as we have had before. But this also works if we, for instance, say that y is a Bernoulli random variable. So it can take values 0 or 1 with a certain probability. And this is exactly what can help us with our classification problem. Because if we say that our response that we want to fit, so here in our binary classification, it is exactly 0 and 1, just as a Bernoulli random variable is. And this is what will help us then to classify our observations into the corresponding groups. And this is also the idea of logistic regression, which is a very special case of generalized linear models, in the sense that it uses a Bernoulli random variable as a response. Then we know its expected value is simply a probability, so p is between 0 and 1, which will help us to then classify our fitted values or use our fitted values by interpreting them as probability and then using it to classify our observations or our fitted values into the groups, saying that if something has a high probability to be of, for instance, species Iris setosa, then I will classify it as such. And the link and response functions that are used in this logistic regression are given here. So this here is the logistic function that you've just seen. This is the response function, and the link function is the so-called logit function, which is given as stated here. So basically, logistic regression is then using ordinary linear regression and then putting the expected value into relationship with the fitted linear predictor from our linear regression using one of these two functions. This is what logistic regression does. It's in theory, you could then fit the optimal parameters beta for our logistic regression using not ordinary least squares as an ordinary linear regression, but with so-called maximum likelihoods methods, which and an optimization algorithm. But I don't want to go into details here in the summary video. If you're interested in that, just look into the lecture notes. I have written it out in more detail there. The point is, in R you can easily do it with the generalized linear models function, so with the GLM function, which works similar to the LM function, which you know from linear regression. It just takes a data argument and it uses a formula to describe what is the response, what are the predictors, and then you have to state what family you use, what is the response variable. And here we've already said we want to look at Bernoulli random variables, which is a special case of the binomial distribution. So that is the family we're interested in here. And then, as with the linear models, you can use the function predict to calculate the fitted values. The only difference here is that you have to state whether you want to get the response or want to get the link, the corresponding link values. So you have a link function and response function. You can state the fitted values using either of those two. And this is why here you will have to say, I want to look at the response. And once you've done that, once you've fitted that a GLM or a logistic regression or logistic regression model, then you get probabilities, right? You get probabilities of belonging to that group 1. And then you can fix a threshold to say, I don't know, if my probability exceeds that threshold, then I will classify that observation as of being group 1, and if not, I will classify it as being of group 2. And if you do that, here I have stated like a neutral threshold, which is 0.5. So if something exceeds the probability of 50%, then I will classify it as being in group 2, which is done here. And in our case, for this iris data, it gives us a perfect classification. As you can see here, here the colors represent the predicted group, 0 for the red or for the orange, I don't know, red or orange points in any case. For these points here, which are also truly of group in group 0, so these here are all correct. And these here are all correct, and what you see in between here is the fitted function. And yeah, this is basically how logistic regression works. This is how we can do classification with it. And what we want to do next is then how to assess the quality of our classification. Because as you can see here, we can now fit a model, we can classify predictions as being of one group or the other, but we still need to assess whether our model is good. But before that, as in every week, I owe you a dinosaur. And last week I've showed you this dinosaur, and I've been thinking about how I could even improve this. In my opinion, this is already almost as good as it gets. I mean, what could be better than one dinosaur with having these hands or using this tool as hands? But then I've been thinking, clearly what is better than one dinosaur with pliers? It's two dinosaurs with pliers. So I kind of been transforming this a bit, just reflecting the points a bit, so to have a dinosaur have a dinosaur whose body goes to the right, and then I've created a second dinosaur by reflecting that again, and then I created Dinosaur Wars. So here we have two dinosaurs which are fighting with each other now that they have new tools to do that. And a couple of things you may want to notice about this is that first, this blue line here, this is of course a perfectly drawn river. So these two dinosaurs are fighting across a river. And what is more important is that it's the logistic function, if you have noticed. I've transformed it a bit, but in essence it's the logistic function. So here you have again a perfect application of mathematics to draw these kind of amazing pictures. And of course I also added a sun here, which is always every school kid I think knows that needs to be in the top right corner. So there you go, there you have a sun up there. I've been inclined to also add some rays here, but then I was too lazy, so I didn't do it. And yeah, that's my masterpiece. I really have to figure out what I do next week. But for now, this is as good as it gets, and I'm pretty sure that no 5-year-old could draw it any better. Okay, so this has been Dinosaur Wars. Let's go back to more serious issues. Let's go to confusion matrix. If you do a classification, then you can, more appropriately a binary classification, then you can classify your observation as being of group 1 or group 0. And then you can, if you already have that data, you can compare it to what is the true classification. And with that you will always get a true or false value. So either my prediction was correct, so something was of group 0 and I predicted as such, or it was of group 0 and I predicted as group 1, and then you can do all of that again with group 1. So instead of group 1 and group 0, one speaks of group of positive and negative. So for instance, in our case, 1 could be positive, 0 could be negative. And then I could compare, is it actually positive and did I predict it as such? And then I get numbers here. So here I will count how many times something is actually positive and I predicted it as such. I would call this the true positive numbers. If I predicted something as being negative but it is actually positive, and I call this the false negative numbers, and so on. So here you have false positive and here you have true negatives. All of this is of course dependent on our threshold that you use to go from the probabilities to the classification. So all of these numbers which you will get from your classification using your threshold will of course change if you also change your threshold. And because it's kind of hard to keep track of the changes when you go from one threshold to the next, there are usually a few classification metrics that use these values like true, positive and so on to compute one single value, and then you can change the threshold and see how that classification metric evolves, and then you could pick an optimal threshold with respect to some classification metrics. So what are common classification metrics? One of the probably most intuitive one is accuracy. So you just simply check, okay, when have I predicted correctly in both the positive and negative cases? So when did I always get a true classification? And I divide this by the total number of observations. So this would correspond to this formula here, and would correspond to the fraction of correct test results, that is positive for the positives, as classifying positive for the positives and classifying negative for the negatives. To make it more applied, you could think of trying to diagnose a disease with a medical test. Then you could think of positive being as a positive person has that disease, and a positive test says a person has that disease. And with that you could interpret the accuracy as the fraction of correct test results, so positive for people with the disease and negative for people without the disease. But this accuracy is not enough, because for instance, depending on your data set, you could get a really great accuracy with a really bad classifier. For instance, if you want to diagnose a really rare disease, then you might test it often, but you will rarely meet someone who actually has that rare disease. And therefore, if you take this data set collected via this procedure, then you will have a data set that will contain a lot of people who don't actually have the disease. And then you could simply take a classifier that simply applies to all observations, just having not classifying them as not having the disease. By the fact that there are only so few observations where who actually have the disease, if you use the accuracy, this bad classifier will have a really high accuracy, because it will be right a lot of times, because most of the time people don't actually have that disease. But this is often not really what we want to do, so or at least it distorts the picture. And this is why there are other classification metrics that use these values a bit differently, and so that you can actually check whether your classification is good and not simply is good because the data set is just has a class imbalance in it. So the class imbalance is just having only a few values of that one group and a lot of values from that other group. This is what class imbalance is, and accuracy is prone to be highly affected by this class imbalance, and this is why it's not enough to look only at accuracy. So this is why there is sensitivity, specificity, and for instance precision. There are way more than that, but these are the most common. Some of those have multiple names. So for instance, sensitivity also goes by the name of recall and true positive rate, and the formulas are given here. So sensitivity is the true positives divided by the true positive plus the false negative, so divided by this whole row here, or the sum of that row. And sensitivity is basically the fraction of correct test results among the sick. So the trues here among the actually positive, so among the sick people. And specificity in return is the correct test results among the healthy. So here we have the true negatives divided by true negatives plus false positives, so divided by that rule. So it's the fraction of correct test results among the healthy. So by changing these, so basically by changing the denominator, in here, or by looking at different groups, we make sure that we are not as highly affected by class imbalance if we look at all these classification metrics simultaneously. So it's always a good idea to look at more than just one value, as I hope you know by now. It's the same thing with the p-value. Don't only look at the p-value in hypothesis test, look at the assumptions and all other stuff as well. And with classification, it's the same thing. Don't just look at one classification metric, just try to get the big picture looking at multiple metrics. And one metric that tries to combine a couple of those other metrics is the F1 score, which tries to address this issue of class imbalance. So it's looking at precision and recall. So at precision is defined here, also known by positive predictive value and by the sensitivity. And it tries to compute it in this way. And with that, it hopes to be not as affected by class imbalance as, for instance, only looking at recall or only looking at precision. One critique of this particular metric is, for instance, that it completely neglects the true negatives, because neither precision nor recall use the true negatives. And depending on your application, that could be a bad thing. So it's not a good idea to simply use F1 score all the time and then think of this as the perfect metric and only use that. Okay. So how do we compute these things in R? It's since the yardstick package, which is also part of the tidy models package or the tidy models meta package, we can easily compute all of those. Probably it was easy before that too, but I'm using the yardstick package, and I think it's quite neat. So using it, we can simply compute the confusion matrix with the conf_met function. So for instance, here we have a prediction. So let's talk about what's happening here. In this tip default, we look at a different data set than the iris data set. It's a data set containing financial information on people and whether they defaulted on their credit card or not. And it's a fictitious data set, but still we want to use this data set, or in the lecture notes we used this data set to run a logistic regression and determine whether from the balance on their credit card, and I think the student status, whether they defaulted on their credit card or not. And so here we have a model, so we classified people as either defaulting or not, and with this classification, we can simply compute the confusion matrix by stating what is the true value or the true classification and what is our estimated classification. And then it simply states the confusion matrix as in the form we just saw. And again, if you change the threshold from say 0.5 to 0.25, then the whole confusion matrix changes. So you see all of those values here, they change. And again, it's kind of hard to see how all of these changes take place. So you would have to look at 4 numbers simultaneously and then for different thresholds compare all of those, which is messy. So this is where the metrics come in. And with metric sets in the yardstick package, you can simply say, okay, I want to compute a couple of metrics, so I will collect them in a set, in a metric set, and here I want to use accuracy, specificity, recall, precision, the F measure, and the Matthews correlation coefficient. You will get to know what these are in the exercises. And if I've computed it as a metric set, then again I can simply use this new function I've basically created now, and then again give the data, give the true value, and give the estimated value or the estimated classification, and then it will compute all of these classification metrics. In the lecture notes you will find how we used this function to compute the metrics for very different thresholds, and then saw how these evolve for different thresholds, And then, for instance, if you want to optimize the Matthews correlation coefficient, then you could simply pick that threshold where this value is the highest. That would be one way to do it. A different way to estimate or to look at classification, or how to see how the threshold affects the classification, is to look at both sensitivity and specificity simultaneously, and this will give you the so-called receiver operating characteristic curves, or ROC curve, or I think maybe you can pronounce it ROC curve. In any case, with the yardstick package you can simply compute this curve, and it will actually apply so here we have a data set which gives you the probabilities, and will actually apply basically all thresholds from 0 to 1, or a lot of thresholds from 0 to 1, and see how sensitivity and specificity evolve, and then you can use that tibble you will get back to call autoplot, and this will create this ROC curve which plots sensitivity against 1 minus specificity, and then you will always get something which looks monotonic like this, so the black line here. And this is kind of an overall picture of our classification performance. If our classifier were really bad, or would just at random classify observations as either being 0 or 1, so being in the group 1 or being in the group 0, just by flipping a coin, then the ROC curve would look like the dashed diagonal here. So in essence, what we try to do is get the ROC curve of our classifier, of our classification, as far away from the diagonal as possible. More precisely, we try to get it as close as possible to the red line here. So this would be the ideal ROC curve. That is just this red line here. And in our case, we could now try to find an optimal threshold that is relating to a point around here. So the point of the sensitivity and 1 minus specificity pair that lies as close as possible to 0, 1. To 0, 1, that's the point here. And if we compute this, if we try to find it, we simply have to minimize the distance from this point to all the points over here. And if we compute this, then we would see the corresponding threshold is 0.03 in this case. And for instance, then we could say this is our optimal threshold for our classification, and we could use that one. A different way would be again to optimize the specific metric as done before. And yet another way would be to go away from these classification metrics and go back to the true negatives, true false, false positives and false negatives, to use these classifications or these numbers, and to think about, okay, what would happen in the real world if I classify someone as defaulting on their loan, and what happens if that person then is really defaulting, or would really default, or it wouldn't. What kind of monetary effects could that have on my company? For instance, if I'm a bank and trying to classify my customers as being defaulting or not, what kind of real world effect could I get from that? And then if I use some scenario analysis, basically I'm saying, okay, the true positives give me $1,000, the false positives will give me $2,000 or whatever, and the others will actually give me a profit of minus or negative 500 or whatever. And then I could use that formula, or I can sum that up and maximize basically my profit. That could be one way to find the optimal threshold. Yeah, so these are multiple ways you could do it. The details, as always, are in the lecture notes. We've done all of that with the specific example of this default data set. And one last thing I want to mention is that from the ROC curve, you can also get another measure of your classifier or your classifier performance by computing the area under the curve. So if we look at our ROC curve again, then we could compute the area below this black curve here. And ideally, this would get as close to 1 as possible because the area under the red curve is just 1. And also it should be way larger than 0.5 because that would be the area of this triangle here of the dashed line. And in a sense, I can get a metric for my classifier by evaluating what is the area under the curve, which brings us to the AUC value, so the area under the curve. And we can simply compute this with the yardstick package by the ROC AUC function. And in our case, we have quite a high area under the curve, 0.95. So in a sense, we found a pretty good classifier in the lecture notes. And yeah, that's basically all I wanted to say. So we learned how to do logistic regression, and then we were talking about classification metrics and also how to use, for instance, something like area under the curve to, for instance, compare different classification procedures. So you could, for instance, take a different classification procedures here and then compare the two AUC values and then go with the classifier that gives you the highest AUC value. And yeah, that's it. And then yeah, see you in the next video. Bye.